up to tonight. Okay. So what happened here? Let's see the error. The value in the graph should be finite, which means that we got infinites in some simulation. So it means that the k value was not good. So let's go back to the inverse of the time. And probably we have to decrease these values here. So let's try with one, let's try this way. I'm just, guessing. Takes some time, which is strange, but let's see. Okay, let's, yeah, oh, you see that we are getting something more meaningful. Good. So we're getting a bit closer. Still is bad. But, okay, let's try to improve it. Now you see that there is a response to rainfall. You see that the low flow is fine. The high flows, still there is limited capability to get the high flows. So, let me try by the low flows are given by the quick flow, by the slow flow. So, while the peak flows are given by the quick flow. So, let's try to keep 4000 unchanged and let's try to reduce this. So, to increase the speed of the quick flow. Let's see what happens. I'm not sure. Yeah, you see that we obtained what we wanted, but still it's not very good. And let me try with this. Now it becomes complicated. When you get close, it becomes complicated to get the right values. Okay. At this stage we are quite close, and now it becomes tricky. Okay. Now another thing, because now it becomes also important to play with alpha and beta, and but still we could get some. We could make some attempts, and I think that in some situations still slowly responding, not very sensitive to peaks. There are a couple of peaks overestimated here and here, but then the others are underestimated. So I think we could try to change alpha, to give more water to the peaks. And let me try to put alpha 0.1. Because I don't know in what direction should I change alpha, so let me try with 0.1 to see what happens. I think it is improved. I saw that it's improved from the value of the sum of squares. So you see that it is decreased. So it is improved, and also if I look at the graph, it is improved because I gave more water to the peaks. So in general, it is improved. But now it becomes really tricky to. And there is one other thing that I wanted to tell you, and this graph, it's not easy to interpret, to understand, because there are many points. And when you are in a similar situation where the hydrograph is difficult to read, is not legible, there is another graph that can be used to compare observed versus simulated data, which is more helpful. And this graph, let me try to substitute this with another one. So, but to do this I need to go back to the code. Okay, let me go back to the code. And instead of drawing this graph, and let me comment everything here. Okay, let me now plot. Let me copy the plot instruction and change it. So, let me try to do this. then I tell you what I'm doing. Okay, so simply I'm plotting the observed data versus the simulated ones. Let's try to see what happens. I just changed the plot in the code, and I'm plotting Qt versus QoS. Let's see what happens. First, I need to re-upload the code. I go back to find the instruction to re-upload it. Fine, and let me redo the last simulation. I just redo it. This is the result. It's a cloud. It's called a dispersion diagram. It's a dispersion cloud. Here you see simulated data, and here observed data on the vertical axis. So this cloud, what does it suggest? First of all, keep in mind this graph, if the simulation is perfect, is a straight line. It's a straight line because if the simulation is perfect, simulated is equivalent to observed. So it's a straight line with a slope of 45 degrees. The fact that you see a cloud means that there is uncertainty. But what is immediate to see here, first of all, here there is a problem with the scale. We should make the scale consistent, the same scale. But in any case, if you look at here, what you can see is that there is, in general, the observed data are greater than the simulated ones. So there is, this graph shows that there is underestimation in general. And, but in order to make a very good comparison, we should improve this graph to make the scale consistent. And we should also display the 1-1 line, which means perfect model. Let's try to change this. After making this change, I stop and I get questions from you. Okay? So let me change this. I go back to the code. And here I need to put limits for x and y. So basically, the limits should be xlim is equal to, let me use this. The same limit that I used for the other graph. Okay, good. But let me use the same for y limit. I want the same scale. Good. And then I need to write the 1-1 line. And let me do this. Lines. I need to create an abscissa and an ordinate that are equivalent. So let me make a sequence from 1 to the max. I added 2 parentheses to the previous line. And let me see. And then I need to put the y, which is the same. I'm not sure it works. Let me try. Let me try, and then I'll show you the code again. Okay? I upload it. Let's see if it works. I am not sure whether it is correct, but let's see. Okay, it's not valid the x limit. Let me go back and try to see what's wrong here. So okay, I forgot a parenthesis. Now it should go. Let me see. Be patient, I need to make a correction again. Let me, I need to look back at the error, the type of error that I got. Okay. 2 must be of length 1. You see that the graph that I got was fine. And there is an error in the instruction lines, and let me do like this in order to simplify the thing. Let me see whether if I put 150 here, sec 1 150, and then sec 1 150. Okay, and then okay, let me see if it works in this way, because I'm not sure. Okay, now it works. Let me comment on this. Let me comment on this, and then I go back to the code and I will show it to you. Okay, so the 1, 1 line is the line of the perfect simulation. What we see here is that there is an overestimation in this region, and the overestimation, why overestimation? Because observed is greater than simulated. So in this region I have an overestimation, and this region is from 0 to 70. And then when I pass to the region of the highest values, there is an underestimation, because the observed is, in this case, the observed is higher than, the observed is lower than the simulated. So if the simulated is higher, which means an overestimation. In this case was the opposite. So this underestimation here in the low flows, overestimation in the big flows. So what I need to do is to decrease the peaks and increase the low flows. This is what I can understand from this graph. And you see that it's very useful. In order to make it, yeah, please.
This graph shows us the problems between the red lines that we modeled before and the black ones.
Yes,
so
yes.
It describes with low flows and high flows where is the problem.
Yeah.
Okay.
This graph is an alternative to the plotting the idle graph, because I think it is more understandable. And this is also required in scientific papers sometimes. If you just show the idle graph and the reviewer says, please put a scatter plot, it's also called dispersion diagram scatter plot, because it is more helpful. And in order to make it more legible, I think we need to make in red the 1, 1 line and to increase the width. So let me do it, and so I can show you the code. Let me go back to the code. This is the code, and just here, let me put line width equal 3 and the color equal red. So these are the two instructions. Let me isolate them. Basically, what I did in the first instruction is simply a plot of points, and I gave the x and the y. So if in the instruction plot you give an x and a y, then it becomes a xy plot. If you give just the x, it becomes an histogram, like an histogram. And you display it with a line, but it's like an histogram. And therefore, what kind of x and y did I do? Basically, qt and qos. And there is a complication because I wanted to set the axis with the same length, and the length should be the maximum between qt and qos. And therefore, this is the reason of this complication. And then the second instruction draws a 1-1 line. And it is a 1-1 because you can see here is x and y are the same. And I had problems in identifying the maximum value, so I took a shortcut. I put here 150 as extremes of this line. And of course, the maximum value can be derived by using the same instruction that I used above, but there was a mistake. I didn't want to confuse you. So let's take it in this way. It's fine for me for now. So what I did, I changed the plot. And then I will redraw it to show you that with a red line, a thick red line, understanding is better. Questions? Questions, curiosity, perplexity, whatever. I'm not moving forward if I don't get at least one.
What did it change? What is changing between this scatter that you plotted and the one of before?
You mean the ideograph or this one?
Because you plotted two different scatter graphs. I didn't understand what was the difference.
Okay. The difference was that in the previous one, the scale of the abscissa was different from the scale of the ordinate. And I didn't draw the 1-1 line. So it was difficult to understand if there was overestimation or underestimation. Just that. Another question.
Excuse me, for drawing the second graph with the command plot qt, you can draw it?
Say again the question. The second graph, what do you mean the second?
Because you show two graphs.
You mean here?
No, the plot.
Ah, okay. The first is the plot of the points. And the second instruction is just adding a line.
For drawing the cloud
Yeah.
graph, with this command plot qt.
You mean comment? You mean these lines here?
Because I don't understand for drawing the cloud graph, for which.
Yeah, the cloud is drawn with the first instruction. You can remove. The second instruction is this one. Just 1 second. You can remove it. And this one is not useful. This one is useful only for drawing the straight line. Is it clear? Okay. Another question. Another question. I mean, I think you should have questions. And I understand that, you know, asking questions is something nasty. And I don't want to insist too much, in the theory especially. But here, I'm tempted to insist. Other questions?
Excuse me, for the cloud graph, is related to the low flow and the high flow.
Yes, because if I go back to the graph, let me draw it again. Let me save this and let me re-upload. I clear the screen, or let me keep the same screen. So let's see the graph. Now you see that with a red thick 1-1 line, the interpretation is better. So here, what do we have on the axis here? It's important that you fully understand this graph. You have to get a full perception. What is this? Okay, with the ideograph is easier. because we have time and flows. It's easy to understand. So what is displayed here? We have on the abscissa, the x, we have the simulated flow, which ranges from 0 to the maximum, and the maximum is something around between 150 and 200. What do we have in the ordinates? We have the observed flows in the same scale, because we wanted it to make the same scale, and this is replying to the questions that we got before from you. Okay, so first important thing to understand, if the simulation is perfect, we reduce to the red line. Good. If the simulation is displaced in a different way, not on the red line, it means that there is a mistake. So let's concentrate on this point here, this one. What does this mean? If the simulation of this flow, which refers to one time, we don't know what time it is just one time, was perfect, the circle should be on the red line. It's not on the red line, it's here. What means? It means that if we go on the ordinates, the observed flow is higher than the simulated flow. You see here it's about 60, and here it's about 85, 75, which means that it's above. Above means that observed is above simulated. All the points that you see here above the red line mean that observed is above simulated. It means that there is, by the model, an underestimation. And this is extended in principle to this region here. Where you see black means a lot of points. And in this region, there is underestimation by the model. What is this region? It's between 0 and 75. It's low flows. Now, let's look at the points that are below the red line. Okay, there are some of them in the same region of the low flows, but not many. You see that it's not so black here. Here it's fully black. Here it's not so black. The majority of the points below the red lines are in the region between 100, this is simulated actually, 150. It means that for the higher flows, from 50 to 100 of the observed, we have the model that is overestimating. This is why this graph allows us to get an indication. Still we are trying, still we are moving forward with a trial and error. Okay, now we have two options. Either we continue with trial and error, but let's make an attempt, okay? Let's make an attempt to continue. And let me clear the screen. Let me try with this. Let's try to reduce K slow. Let's see what happens. First, let's look at the sum of squares, which is okay, like before, more or less. And this is the graph.
You said that we are trying to reduce K slow.
Yeah.
But in the text of our file, K slow is the first parameter.
Ah, okay, maybe.
I don't know
Okay,
if
sorry.
it changed something or...
Yeah, okay. Okay, that's fine. And it was a mistake by me. Let's say that I didn't, the first consideration was not very effective, but I changed the other K. And so basically, sorry, here I am. Let me try to change now this. 110. The result is not good. You see that the sum of squares is increased. Let's look at the graph. Yeah, definitely it's not good. Okay, let me go back to the previous one. But now let me change beta. Let's put it 0.1. Let's see what happens. Beta is the only parameter that we didn't change. The result is not good. You see? Let's try to change beta in the other direction, 0.8. Now the result is better, but still it's not much improved. Okay, now we understand that indeed it becomes a bit tricky. Even if I think this is the best result that we probably got so far. And keep in mind that if we look at this simulation, now you see that in the low flow region the situation is improved because we have a mix of overestimation and underestimation. It's more balanced. And keep in mind that the model will never be perfect. So at a certain point we get to a stage where we cannot improve more. Okay, now let's try with the automatic calibration by keeping into account that this is the best result where we got so far. Okay, so let's say, okay, I'm not very happy, but I'm not also much disappointed. So let's see if I can improve starting from here. And then we get into the domain of optimization. And optimization means that we ask the computer to make several attempts independently of us, and we ask him to judge the goodness of the fit by looking at the sum of squares. So the plot is not needed anymore, even if we may wish to have a look at what happens. So let's say for now, let's move in the domain of automatic calibration by keeping also the plot. So first we need to identify a function in R that performs automatic calibration. And we said, and Nicola also had a question about, we said that Optim may be a candidate. Optim is, what does Optim do? You may look at the help, but basically Optim needs a function to optimize. In our case, the function is our IMO function. The function is supposed to give back an objective function to be minimized. In our case, the objective function is the sum of squares. The function has argument only a parameter vector. It's our case. Argument of IMO is only a parameter vector. And the optimization function changes the parameter vector by making several trials. Each trial, it looks at the objective function and finally stops when it believes that an optimum was reached. And the optimum is the value of the sum of squares that is optimal. It will not be zero, because the model will not be perfect, but it will be hopefully lower than the value that is given by this simulation. We should also be able to tell the objective, to tell the function, the optimization function, to start from this baseline. So not starting randomly, but in this baseline. Hopefully, we would like to be able to give to the objective function the range of the parameter values to be explored. We don't want the objective function looking at every possible value of the parameters because it takes too much time. We want to tell it, look for the values of Cmax, for instance, in the range 0, 400. We want to give ranges. Okay. So First decision that we need to take is to identify the objective function. A candidate is optim, but it's not the only one. There are several options in R. I feel very comfortable with another function other than optim, which is a bit more complicated because, but I think it is more efficient. Why it is more complicated? Just because it's not embedded in R, we need to upload it. And I think this is worth doing for two reasons. First, because the function is more efficient. Second, because we learn how to upload external functions in R. We already learned how to upload an external function because we uploaded imode, which was done by us. But there is another option. So let me talk about this. What are the options to upload external functions in R? There is the first option, that is what we did. And basically, we uploaded a function that we took from the web. The web was my website, but it's something that we were supposed to prepare ourselves, but we decided to upload it from my website because it was quicker. In the same way, we could have found it in other websites. So you may find a function on the web, whatever, and you upload it. Keep in mind that in doing that, you take the risk of getting something prepared by others and using it. So in my case, in our case, you trust me, and then you said, okay, that's fine. The professor says and he is responsible for it. So if it is wrong, you come to me and say, Prof, you told us to use your function, it's wrong, it's my responsibility. If you take another function from the web, from whoever else, you can't give him the responsibility, him, her, the responsibility if the function is wrong. You take it. Keep it into account, meaning that anytime that you use a program, whatever, even when you use Excel, you are taking the responsibility for any mistake that the program can make. And you can't waive the responsibility to Microsoft if you design a skyscraper and then Excel makes something wrong. By the way, if you look on the web, bug Excel, there are several examples of computations that you can make with Excel wrong, where Excel gives wrong results, because any program is bugged. This was, in the past it was like that. There was examples that were really a lot of fun. Maybe that today, they improved it. So I'm not sure whether you can still find examples of Excel bugs. But in any case, you have to assume that any program contains bugs. If you make your design and then the skyscraper falls down, you cannot say, yeah, all the responsibility is Bill Gates because I use this program. It's your responsibility. When you put your signature on a design project, it's your responsibility. So keep in mind that when you take something from the web, wherever you take it, you have to be aware of the risks. Of course, the risk decreases when you deal with Microsoft, when you deal with something that is controlled, that undergoes the quality control. If you take something from my website, it's not quality controlled, so the risk is higher. And also, keep in mind that the larger the number of users, the higher the quality of the program. This is a general rule. So if you take something that has only a few users, you are almost sure that there are bugs. In the case of Excel, there are millions of users, maybe billions of users, and there are billions, yeah, maybe. And then, it's more quality control. Okay, so I talked about the first option for uploading function in R. There is another option. R has a repository of functions that can be uploaded. The repository, it's a website, nothing else. It's the same repository where you download R. And the advantage is that these functions that are uploaded in the repository are controlled, reviewed by the community. They are not just uploaded on proposal. If you make a new function in R that you want to upload on the repository, you have to submit it. There are people reviewing it, and then at the end of the story they say, no, sorry, you can't because the quality control test had failed. So you have some quality control if you get function from the repository, which is better. So your first question, when you need to do something in R and you don't have the function, embedded in R, the first question must be, let me look at the repository. There is in the repository a function, the function that I'm looking for. If yes, it's better to take it from the repository. If in the repository there is nothing, then you look for maybe somewhere else. Okay, how to know the content of the repository? You can search for it, but usually what I do is I go to Google and then I say optimization R project. I would say R project, not R packages. And then you get a lot of things, and then by looking at these links, we don't do it now, you learn the name of the function. And of course, you may also look at the references, at the comments by the users, etc. Now, let's suppose that we already identified the name, and the name of the function I want to propose to you is this one, de-optim. I don't remember. I think it is in capital. Yes, you see, the first link, CRAN, CRAN is the name of the R repository. You may remember this name because when you downloaded R, you already saw this name. And you see that in the repository, it is nominated a package de-optim. Okay, good. This is what we need to upload it. We need the name.